We gaan verder in het Engels, omdat onze opdrachtgever uit Engeland komt. Hij is, we vertellen nog wel wie hij is. So we will now continue in English, and this is the title of our project. It's function approximation, specifically transcendental function approximation on the ARM Cortex-M4. And there's a lot of specific words in that. So we will explain that in the introduction, and we will explain our setup, so our schedule of how we are going to tackle this seeming very difficult task. We will explain some of the theory behind the methods we at least try to use to come up with products. And then we will discuss our products, which well, we have an original program and we have two products which we can compare to the original to see what is best, and then we'll make a short conclusion to that.
So the man who we are doing this for is Professor Ferber. He's a professor at the University of Manchester in the UK, and he's doing the SpinApe project, and that's a project which consists of building a neural network out of a lot of ARM cores, and a neural network is like a model of the brain, which will compute tasks like a real human brain. It will do this on the ARM Cortex-M4, as you might have seen, and the function used in a lot of neural networks is the sigmoid function, which we will show after this. And so our task is mainly to get an efficient approximation of the sigmoid function, because this is very expensive to compute on a computer processor.
So expensive means that it takes a lot of time to perform all the calculations needed to calculate the result to the function. This is Professor Ferber himself.
And we know him from his computer file videos, in which he talked about how he designed the first ARM processor, which is a type of architecture used in most mobile cell phones today. So that's quite an achievement. And so the theory about this is this is our sigmoid function, and so we will be approximating this. If you were at our last presentation, you might have already heard about this, and we will approximate it on the ARM Cortex-M4, and we don't have one. We have some ARM cores, but those are not the real M4, and so the tasks that the ARM Cortex-M4 can perform aren't the same as these, but we looked it up online and we compared all the instructions to the calculations we have to make.
Right, so the setup, like how we're going to do this, was we thought of how all computer programs are organized. Like when you write a computer program, you write it in a language that's readable, as readable as possible for a computer program to humans, which we call a high-level program. And then usually you use some kind of, it's called a compiler, which is a program which translates the high-level human-readable program into something that a computer can read. And the computer reads ones and zeros, so that's not something that you can write as a human. And in between those, there's a language category which is called low-level programming languages, which is well, assembly and some languages that look like high-level programming languages, but that's like in between. Like it's a bit readable for humans and it's very close to readable for computers. So we made a plan to consider each level of programming language and think, like, at this level, could we accelerate? Could we do something to accelerate the program? So can we speed this up at this level? So we considered each of them, and it appeared that, well, mostly the high-level approach was most useful. And the high-level approach was using, there's a whole mathematical branch called approximation theory, which uses things like interpolation. Now, the principle of interpolation is that you have the original function, which is very hard to compute, and you store some of the results of that very complicated function in a table, which is just a list of numbers. So it's essentially some coordinates, and then there's a hopefully easier to compute approximation formula, which is the interpolation formula, that you use to calculate, to make a graph that goes through those points that looks like the original function as much as possible, of course, but is easier to compute. And well, so we decided, we considered all levels, but we decided to go for interpolation.
So the original program is what you can see on the right here. And when you look at this, you can see this is just how to display the formula, and here's the actual calculation. You can see there's an e raised to the x, so just like in mathematics where you have an e to the x, and that's the part that's very hard to compute because it contains, of course the x doesn't have to be 1 or 2, but it can be in between, and then you get a very long approximation to get the real answer, and that's what takes a lot of cycles in the processor, because one of those processors will just iterate on a certain operation like adding or subtracting, and one of those e to the x's takes a lot of time to compute. You also have a division here, which is also very expensive to compute, so you don't like to be continually performing those operations very often for every single point in your graph. So that's why the sigmoid is very expensive to compute. You can see it here, and here's 0, here's 1, so it's a smooth transition into to 1, and here's the y-axis right through the middle. Now, if we look at a linear interpolation, which you might have seen, it's when you have 2 points and you just draw a line between them and then calculate it like that. That's also pretty expensive to compute. You can see it here. We map the value from a lookup table, which is generated here. So first we calculate some of the values in the traditional function, and then we have those, and we don't have to calculate them later when we are actually running the program. So we will use those values to calculate the 2 points and then just draw a line. When you analyze this, you can see it will take 29 cycles when you get one for 1 point to calculate 1 point, and we didn't show it, but the original function would take around 200 or more cycles to only have one answer. So this is an improvement, but it's also still quite expensive, and you also need to calculate a lot of points in the beginning to actually be able to get a reasonable approximation, which is also you have to wait a long time before you can actually start running the program.
Right, so this is the first really, because the actual task was to find a non-linear interpolation algorithm. So this is the first real product. The other one was just to show like why you shouldn't use linear interpolation, because it's quite imprecise in comparison with the other two products. First of which is polynomial interpolation, which uses a polynomial. So this is the actual program. It's already a bit longer than the other ones, and this is the actual formula which is used for polynomial interpolation. It's called Lagrange's formula, and well, there's some important things to note here. I don't think you can see it all, so I'll just explain to you what it says. And there's a series of additions, and well, the series of additions, when you translate that to programming, it means there's a loop. Like you do this a certain number of times, and well, each time there's another part of the program that's happening. And within, so these are all the terms in a loop, and for each term there's another loop, which, and you know, each loop means there's like a multiplication of how long the program takes. So loops are very important to look for, because they're very expensive and they take a lot of time to compute. And within the second loop there are subtractions. It's probably just not to read, but there are subtractions and there are multiplications. And we know from the instruction set, so this is a low-level part of the analysis, we know from the instruction set, because the ARM processor is a RISC processor, it takes only one cycle to perform either a subtraction or a multiplication. So those are actually pretty fast, and it will be, it won't be very expensive. More important is, at least if you don't have a very long lookup table, which I will get to later, is that in the first loop, so you have the loop that takes care of the numerator and the denominator, and in the first loop you come back to a whole term, and in that one there's a multiplication and a division, and divisions are very expensive, we know from the instruction set, because they take all 12 cycles instead of one, like addition or subtraction or multiplication. So the nested loops, because it's a loop in a loop, which makes it extra hard to compute, the two nested loops, they take very much time, and the division, which in the program you see only here, this like slash. So that's very like infamous for the program. There's one symbol and the program is much longer. So what turns out, for the polynomial interpolation, because there's a nested loop, the program gets like exponentially much longer with each point you add to the lookup table. However, for the lookup table, it's much better if you have a long lookup table, because then you have more points that you can consider for the approximation to go through, and will have a lower error. So there will be less deviation in the approximation from the original function. But so the lookup table wants to be long, because that increases precision, but it's a very bad idea for polynomial interpolation to have a very long lookup table, because the time it takes to compute polynomial interpolation increases exponentially. Yes. So these are some of the outputs of actually this program. And you see for NX40 and NX20 the outputs. We wrote in the actual report that the best n, like the best length of the lookup table for polynomial interpolation, is 12. and that's mostly because in the middle, when n increases, you get a better approximation, but near the edges, like near the highest and lowest point, highest and lowest x in the graph, you get very large deviations near those points, and near there less more. So that's not a good idea, because if you try to approximate it for a very high or very low x, then basically formula is very useless. So then there's another better thing.
Yes, because polynomial interpolation will, when you have a couple points, will just make one formula going through all the points. But cubic spline interpolation will calculate a different spline. Spline is a formula of this form, so you can see you have a x to the first power, x to the second, next to the third power, with all the possible factors. And so if you have a spline for every single interval, you don't have to worry about the big deviations at the ends of a polynomial interpolation. So in theory, this is much better, and in practice it also is. But the way you calculate this is quite hard, and we didn't manage to actually program an algorithm that does this for us. So we just analyzed the mathematical way to calculate a cubic spline. So this all seems very hard, but the thing to do is we have two formulas in their most undefined way, and then we start applying conditions. This is calculated for a couple of points, so we fill in the points in these formulas, and then we get a couple other formulas. So as you can see, these two conditions are pretty important. These mean that the inclination of the first spline when it gets to a point will equal the inclination of the second spline, which will continue upwards, because otherwise you get like a hard edge on the point itself. So that's something you don't want. And also for the second derivative, they also have to be equal. And then you get here you just fill in the points. You get one of the constant factors already, and then you just start filling that into other equations, and you can just get some equations. So this will be the first equation, this will be the second equation, and so when we get further on, here we fill in, we use the second derivative of the first equation and the derivative of the second equation, and when you just fill in all these things, you get a couple of formulas using only the factors, which will be constant. So that's nice. And then you get some others, and so there's the fifth one. And when you have all these equations, they're just linear equations which you can solve using matrices, and that's not a very hard thing to do. And then you get the two splines for each interval. And so now we have computed splines, and the cool thing about these splines is that we can calculate them beforehand. So we don't have to do all this during the time that the program is executing. And when we have these splines, we only have to see what kind of so we only have to look at where in the lookup table, that means lookup table, and the right interval is. So we have a couple points, and we look at where our x value is in these intervals, and then so we search that for for the right interval, then we get the information about the spline on that interval back, and we can just fill in the constants, and then we get a final answer of only 16 cycles per value for a cubic spline interpolated function. And so that's way less, and also way more accurate than the linear approximations.
So in conclusion, like wrapping all these things up, we found that, well, linear interpolation is a very bad idea. So then the next step is, of course, polynomial interpolation, which is very expensive and imprecise at the edges. Expensive because it gets exponentially harder to compute with each value in the lookup table. Like, we didn't write out an entire program for cubic spline interpolation, mostly because it proved to be very much more complicated to actually create a software implementation of a formula than to just sort of understand the formula. So it's like for cubic spline, we managed to sort of understand how it works, but really making it into a computer program is another thing. So that's why we haven't been able to test it. But analyzing the mathematics, it should be far less expensive, as Anna said, very few cycles, and much more precise, and much more practical since it doesn't use temporary points in the lookup table.
So that's what is, what was it? Thank you for it. Any questions?
Ja, mag ik even terug naar het plaatje met die twee diagrammen? Yep.
Okay.
Could you explain, or could you hypothesize on why it gives such a big spike on the two edges at n is 20 instead of the n is 14?
We cannot. It's probably because this is the highest value, so there are, like here there's much more certainty because there's more values around it that all have a bit of influence on where the point around here should be. But right here there's only the left part of the entire graph, but there's no right part to it. So as far as the approximation, the interpolation program is concerned, a point like here could be anywhere, because there's no telling whether there's something in the formula that makes it go all wild at this side, because there's no information about where a point here would be or where a point here would be, only about here. So the farther you go to the center of the lookup table, all these circles are points where in the lookup table, which is stored in the lookup table. So more in the center of the lookup table, there's more certainty about how the original formula behaves. So that's probably why there's such a large deviation at the edges.
Any more questions? How was that?